Learn about DeepSeek R1's innovative AI architecture in this course taught by Yassine, a published researcher and experienced data scientist. This course explores how R1 achieves exceptional reasoning through reinforcement learning, focusing on group relative policy optimization, or GRPO, and how it improves upon traditional PPO methods. You'll also understand Divergence's role in model stability with practical code examples and clear mathematical explanations.
You probably heard of DeepSeek R1, a new open source reasoning model released in January 2025 that reveals the O1 series of reasoning models. In this tutorial, we'll go through the theory underlying the methodology in depth. The major significance of DeepSeek R1 is that it's effectively an open source implementation of O1 from OpenAI. This is a breakthrough because the methodology for reasoning model was closed source until now. The methods from DeepSeek, as you're going to see, is surprisingly simple and elegant. To understand the paper fully, we will be going through 3 levels of details. First, an overview of the whole paper methodology, which include the reinforcement learning, the data augmentation, and distillation portion. Then, a deep dive into GRPO, or Group Relative Policy Optimization, and its implementation in an open source reproduction from Hugging Face. Finally, an even deeper dive into the key divergence penalty term that is used within GRPO that has a very particular shape. At the end of this tutorial, you should have more than a good enough appreciation of how the researchers at DeepSeek and OpenAI managed to create reasoning models. We're gonna go fairly in depth here, maybe a bit too much. So don't hesitate to pause the video and reread the paper to really absorb all of the information. Let's get to it. Let's start with an overview of the methodology the author used. I found out a really nice map that shows visually how the method is structured because it can be a bit difficult to follow which model is doing what. So if we just take a broad overview of what's going on, we start with the base model here, DeepSeek V3 base, and the whole output is to generate these 3 things. So DeepSeek R1-zero, DeepSeek R1 distilled, and DeepSeek R1. These models are reasoning models like the O1 model from OpenAI. So if we dive into the result here, you can see here DeepSeek R1 is this big blue bar, and you have like these 6 benchmarks, and the TLDR here is that it's very close to OpenAI O1. So close to OpenAI O1 that you could argue that it kind of reproduced it a bit, except on this one. But it's very close in general, right? And it's better than like just the DeepSeek V3, which was the model that is based upon. So the reasoning that we're adding on top of DeepSeek V3 is helping in all of these different complex benchmarks. One thing to note here is that this is mostly just doing post-training. It's not doing pre-training. It's using the pre-trained model DeepSeek V3, which was recently put out, right? So like when you look around and see like the different tech company kind of freaking out about DeepSeek, it's not like the DeepSeek R1 that they're freaking out. It's literally this one, the DeepSeek V3, which is used as the base. Reproducing the R1-zero result is not that complicated, that much. It's this one that is a bit more complicated to reproduce. And where is a lot of the hype is around. So we're not going to go into DeepSeek V3, but like know that this is a mixture of expert model that is also open source. Let's start our little walk through this paper. So we're going to start with the DeepSeek V3 base, and then we're going to go over here, right? We're going to go into this little block, and then we're going to do the reasoning-oriented reinforcement learning, right? To learn reasoning, not through like a supervised fine tuning with human feedback and whatever, just with the reinforcement learning. So just with this and proper reward functions, the researchers at DeepSeek managed to get this model to becoming a reasoning model on par with O1. This is what they did, right? So let's take a look at it. There's 2 blocks that are important here. There's the reward function that they're using, right, or reward system. And then there's this thing, the GRPO that we're calling. Both of these things play together in order to make it so that we don't need a human in the loop or more data here to do what we need to do. So the group relative policy optimization is not coming from this paper, actually. The idea came a bit earlier. And this other paper, so DeepSeek Math, pushing the limit of mathematical reasoning in open language model. So this was in April 2024. And you see here, DeepSeek Math is better at this particular math benchmark. So I think that they seen what they did with group relative policy optimization on the math benchmark, and then they were like, hey, we could do so much more with it. So DeepSeek R1-zero was built out. We're not going to go into this paper either, but like, you know that this is not a new idea. It's coming from here, and then it's very useful. So what's going on is this very huge formula. And in a nutshell, we're trying to do reinforcement learning. And reinforcement learning is quite simple. Is you have an agent of some sort with some policy, which is its parameter, set of action that they can do, a set of state, and then the environment is giving it reward about like, is it doing good or not? And if it's going good, the policy should be updated so that the agent can move through the environment and like get more of the reward and less of the bad stuff, right? In this case, what they're doing is they're trying to teach the model to reason through the task properly and then make it emerge so that like the performance is better. That's what they're doing. And then with a certain format of answer to be put out. Remember, this is DeepSeek v3. So they're trying to make DeepSeek v3 better at reasoning. Very important. They're not trying to make a model that is pre-trained from scratch to do reasoning. Trying to make the DeepSeek v3 base model be better at reasoning. The prompt that they're using is this thing, right? So blah, blah, a conversation between user and assistant. You see it's a very, very tight prompt. And then between here, this is where it's saying like, hey, you should be doing reasoning. Process necessary clausing within think and think here. And then here in think, reasoning process go here. So they're telling the model to follow this format. They're not going crazy in terms of like restraining the model and manipulating it so it does that. There is some reward function to make it stay there, stay in this relative format in terms of think. But this is where in the think that it will output is chain of thought that it will feed back into itself with reasoning token. We're gonna go through the reward model and then we're gonna go back to GRPO. So here, the important point in this paper is that it's a rule-based reward system. So there's no critic model in this part. In the other part, there will be, but in the R1-zero, there is no critic model that is happening. So there's not another neural network that is trained to critique whatever this model is outputting. It's just deterministic reward functions. It's only deterministic stuff. So here you have the accuracy reward on some of the benchmarks. So for example, for lead code problem, there's like, is it compiling? If it's compiling, cool, you get a point. Is it like clearing up the test? If it's clearing some tests, but not others, you get some point. So it's very deterministic. And so this is where the link to the reinforcement learning loop from the environment is. They have this for math, they have this for like the engineering things, they have this for the coding stuff. And then there's feedback loop from the reward system for the format. And the main thing that they're trying to do is like keep your reasoning between the think tag. And that's kind of that. Like this is what's going on with the reinforcement learning loop. So we have this, and then this is getting fed to this formula. That reward that we saw previously, it's this thing. It's the advantage that we call in reinforcement learning, and it's this advantage is just like the rewards normalized, basically, with the mean standard deviation. So keep that in mind, because when we're going to go over here, we're trying to maximize this whole beast over here, trying to get the biggest number here. And then the policy in this setup is pi. And you see here we have 2 pi. We have the old pi and then the current pi. So this is what the parameter that we're trying to change right now. So in this pi old is the parameter that led to the output that we're using at the moment. So you see here we have these O's and then these Q. So for a given question, the model will output many output, right? It will shoot out many of its output. And then these output will have some sort of confidence log probability associated with them. These log probability are in here, right? So this, if we summarize it, it's like, how confident are you about whatever you're outputting in terms of string of text at the moment, right? And then this is multiplied by the advantage here that we're calling, which is the normalized reward. So how confident are you? What's the reward that you get? And you're trying to maximize that technically, right? You're doing a normalization here based on like what the old policy was doing. And then this is what you're doing right now. So you're trying to do better than the old policy. If you're doing worse or you're less confident and whatever, there's like a weight that is happening between these two. So yeah, so if you had only this, it could work, right? But it's going to go all over the place. So what we're doing, if we take the other element over here, you see we have a minimization over there between two things, right? Between what we just discussed, right? So how confident times like the actual reward for like each of your answers, and then this thing over here, which is the clipping. The clipping means, if you look at it, it's exactly the same stuff, right? It's the same stuff as this. Yeah, also have the times the advantage, except that you only are allowed to take like a step of certain size in both direction. And this is a hyperparameter that you can tune if you want to. But what this effectively means is like, don't take too big of a step. That's all, right? They are trying to limit the different movement that are too chaotic that reinforcement learning can occur in the reinforcement learning agent. This is the only thing that this thing is meaning. The second part that you have over here is the KL divergence over there. And then if you look, you have different stuff. You have like the current model that you're trying to improve, and then a ref model, right? And then you have the parameter beta, which is like controlling how much of the KL divergence you want to take into consideration. But the ref model here is a DeepSeek V3 model. In effect, right? KL divergence is like the distance between two distribution, and then the DeepSeek V3 and then this DeepSeek R1 that we're trying to train should not be too far apart. So you should not start to like train and change like your weights and your behavior too much that you're diverging very far away from the base model. That's all it means. So in a nutshell, the GRPO, what it does is that it's doing its work here on with the feedback from the environment and all this stuff, and everything else here and here is just to make the model not go crazy too much. That's all there is, right? So this is with respect to the previous model, to the base model, and this is with respect to the previous old model. Don't move too far away from it. So we're done with this part over here. So we have our accuracy and our formatting. So this is the path that we're choosing. This path over here include that, but is not present in this particular case. And that's kind of that. Just with reinforcement learning, we get the following result. We get DeepSeek R1-zero to be very close to 01 mini and 01 that number in all of the different benchmark, right? And if you look at like the training step for this reinforcement learning loop, we see that the performance goes from like really normal for like a non-reasoning model to reasoning close to the different kind of 01 that we have here, and even surpassing it at this point at like more than 8,000 steps. So this is cool. This is great. The part that is very interesting is this curve over here, right? So what this curve shows is that as the training step increase, the model is giving more and more lengthy reasoning response within its think tag. But in no moment did we force it to do that really. It just learned that like through the reinforcement learning loop, if I increase the amount of text I have in my reasoning, I'm getting better result and more rewards. The only part really where we're incentivizing it to do that is here in the prompt, and it's not too crazy. We're just asking it to reason, and then it's doing its stuff to reason here. So if you take a small look at like what type of response you're, and you can try this by the way with the Olama on your own computer, you can say like, hey, here's my question, and you can see like the taught response. You can see like here it's trying to do its best, and then at some point it's like, hey, wait, there's a high moment I can flag. It figured out something. It go back into its step, and then like it tried to figure out afterwards. So there's something bigger that is emerging from the reinforcement learning loop on this DeepSeek V3 base model that was already trained, right? So it's as if like reasoning was already there in the DeepSeek V3 kind of big, huge model with 600 billion parameter. And then the reinforcement learning loop kind of juiced it up so that that reasoning was more at the forefront. And now since it's at the forefront, you get this type of more intricate behavior. So this is good. This is very interesting because you don't get that with O1. So OpenAI decided to hide the chain of thought, even though it could be useful for you to see the reasoning of the model. It's a choice that they've made. I think it's a good business choice because you could just technically use O1 to distill the chain of thought and generate a data set that will help you create your own reasoning model, so O1 will not be that useful. As we're going to see in the distillation aspect, that part makes small model very, very good. So we have that. The issue that is happening with the DeepSeek R1-zero model, right? At this point, we have a trained DeepSeek R1-zero model, is that it's very difficult to read the chain of thought prompt. It's not made for you, right? It's made to maximize the reinforcement learning loop that we have, which is very interesting. It's using its token to the reasoning token to get to the result. And sometimes it's mixing different languages. It doesn't matter for it if it's say in English or say in Chinese or whatever. What they thought at this point is that, hey, if we are gonna align it a bit better, the reasoning step will be more coherent for people. They will be able to see it better. And technically, if we gear it properly, the performance should be even better because it will have less of a random walk to do in reinforcement learning land before finding the reasoning for real. This is why we're over here. They did at the first supervised fine tuning, right, with some cold start chain of thought data, right? So they had this data. And then they didn't say how many samples. They said thousands. I don't know if it's 9,000 or just one. So they did that, and then they used supervised fine tuning to fine tune this model before doing the reinforcement learning thing that we're discussing. So at this point, they did this supervised fine tuning with this data set. And then they do this, what we call reasoning-oriented RL with GRPO, but they're adding chain of thought language consistency reward. So they're forcing the model to not do this language mixing thing because we can't understand it. There's an interesting tidbit of information here. If you see here, ablation experiments show that such alignment results in slight degradation in the model performance. This reward aligns with human preference, making it more readable. Very cool. It means that the model was better when you could mix the language and stuff. And when we forced it to not mix the language, it was slightly worse than before. Then you have a whole bunch of accuracy, right? Reward accuracy of different things. So the format, so the language consistency, you have the deterministic accuracy about did I get the code wrong or did I get the math problem right? All of this is fed into the feedback loop with the reward. Now buckle up because at this point there's multiple model that comes in. When we're out of this, we don't have DeepSeek R1-zero. You can forget about it. It doesn't exist anymore, right? We have this intermediate model, DeepSeek V3 base, that was trained with reinforcement learning and with supervised fine tuning. We have that, right? What we're doing is we're gonna use that model to generate some reasoning prompt. It will generate the data. At this point in time, its only value is to generate data, right? To get to the other model, we're gonna do something else. We're gonna start with DeepSeek V3 base over here, and then we're gonna go all the way down here for a supervised fine-tuning step, and then again a reinforcement learning loop here, but using the data that we're using. So right now we're on making data land. We're not into training anything, right? We're using that model, intermediate model, to create some reasoning prompt, and then there's another model that we're not seeing here, which is this guy again. It's this dude, DeepSeek V3, and then DeepSeek V3 is acting as the judge. So in this step, right, it's reasoning data, and then before with DeepSeek R1-zero, it was just a deterministic reasoning data. Here they're adding other sort of reasoning data using the judge kind of setup where you have another model that is able to give you feedback about the data that is being generated. Plus they're filtering out some data that is out of whack with like mixed language, long paragraph, code blocks. Yeah. So then you have a data set that you can use for doing supervised fine tuning, like we did in the previous step for this particular model over here, right? So that thing that we're doing, we're going to try to do it again, but with more data effectively, right? We're going to try to do it again over here. So they do that, and they also try to generate non-reasoning data for like writing, QA, self-cognition, translation, and then they still use DeepSeek V3 to generate these. And then they try to generate some chain of thought data for some stuff, but this is not that important. So at the end of the day, you get like 600 and then 200K data set that you can combine. So here you have like the DeepSeek V3, some leftover data that like they could use for supervised fine tuning. And then you have a V3 over here that is using like chain of thought prompting in order to generate some non-reasoning data over here. So 200K sample over there, 600K sample over there. You add them up, and then you have this combined supervised fine tuning data. We're there at this point. Now, what they're doing is doing reinforcement learning on all of this stuff, right? And to do that, I think, you see here, for reasoning data, we adhere to the methodology outlined in DeepSeek R1-zero, which use rule-based reward. So for some of the data set, they're using this. And then for general data, we resort to reward model to capture human preference in complex and nuanced scenario. So there's a critic model in there. So there's this going on. And then they're adding two things to the reinforcement learning. So they're adding helpfulness and then harmlessness. So helpfulness is like, is the output helpful for the user, right? There's some sort of like a metric that you can get out of this. And harmlessness is where you can induce some biases on the model to not talk about certain thing, right? Yeah, this is what's happening here. The harmlessness actually will tank a bit the performance in some of the benchmark because the model will not be able to output the information that deep in its weight it has because it followed, and then the weights are set up in a certain way to not output these things. So yeah, so this is this part. So at this point we're here. So there's this combined supervised fine tuning data. You do supervised fine tuning on the DeepSeek V3 base over here, right? You do that over there, boop, with the 800K sample. And once you supervise fine tune, after that, use reinforcement learning here. So this is where we're doing the preference reward that we just talked about. And through this loop, which is the same as the DeepSeek R1-zero over there, but with like not just rule-based stuff, you get DeepSeek R1. That's how we got the stuff. So if we look at the result here for DeepSeek R1, it's actually good. Like it's not too bad. You see we're over there. It's doing good in like English. It's going good in code. It's doing good here in math. It's doing good in Chinese. I believe like it could have done better here, but it was nerfed. Yeah. So overall, it's pretty good. It's on par with OpenAI. The cool thing that they've done after that is that they use all of these models that are much smaller, and what they did is that they took all of the supervised fine-tuning data that they had, and they did supervised fine-tuning on these, right? They did two things actually. They tried to do that with the full reinforcement learning loop, right? Like so this whole pipeline with the smaller model, and it didn't go that well. We're gonna see in a minute, but like when you use like all of the data based on this, and then you are using this for distillation. So taking this big R1 model in the loop to do the distillation of that model into that, you get a much better performance with these models. So distillation is not too complicated. You have the teacher model over here, right? And then like you have the log probability, you have access to the log probability of like the output, right, of the model as the input are passing, and you have a much smaller model. And then the smaller model, so this is a student. So the student has access to like the input output, right, throughout this, but it also has access to the log probability on the big one. And then they try to mimic that also, right? So this makes the student learn much faster. Distillation is a very like a standard process in deep learning. So with this, right, with this data that was made with this whole pipeline and then DeepSeek R1 distillation, you get Distillate R1 distill into Quen or Llama and then the different bees that you have. And then these, you can go right now in Ollama, like download some of them and start to use them. You can use like the 1.5B over here. It will work in most setup. And here is the result where they tried to do the R1-zero on Quen directly, just Quen, and then distill from R1. And as you can see, the distill is better, and it just seems like the reinforcement learning pipeline on a smaller model is not like as effective as doing it on the much huge models, because remember DeepSeek R1 was made on the 600 billion parameters of V3, right? So it seems like there's the big model, right? And then when you're doing reinforcement learning, it's like you're making like the reasoning core pop off a bit, and now it's doing better. When you have a smaller model, it seems like this reasoning core is not popping off in a meaningful manner or some sort. Like, don't quote me on any of this that I just said, but the feeling is seems to be like this. So that's it. So this is the paper. It's pretty cool paper. I suggest you to read it with the map next to you, because you're gonna need that. But overall, like the core of the paper is really that part, like GRPO. Let's now dive a bit deeper into the Group Relative Policy Optimization, GRPO, algorithm, which lie at the center of our R1. So the Group Relative Policy Optimization algorithm appear here mainly in the DeepSeek R1-zero path. It's different from the previous algorithm that was used for reinforcement learning from human feedback, which is PPO. So we're going to quickly go and check out like the difference in the formulas. So most of the information I'm going to show you doesn't come from DeepSeek R1, it comes from DeepSeek Math. This was published a while ago. Here we are, we have the PPO algorithm, which is the classical one that was used for reinforcement learning from human feedback. And then we have the difference with the GRPO. The PPO algorithm, I highly recommend this video, right? Proximal Policy Optimization, PPO, how to train large language module from Cyrano. Absolutely awesome. Like it goes very slowly, step by step in each of the step of the algorithm. So in PPO you have two models. You have the value model and then the policy model. And then in a nutshell, the value model is like what are the values for each of the place in the grid, each of the states that you're at in. And then the policy model is like at each of the states, like what's the probability that you go in whatever direction. So you train these two things in parallel using the gain, which is like the difference between what you said it was and what it actually was. So that's kind of the idea. What GRPO is saying is that you kind of don't need the value model, and we can bypass that and then just use the policy model to approximate the advantage, and we should be good to go. If you take a look here, the value model is going to output the value, and then these value through the generalized advantage estimation over here will generate what we call an advantage, which is like some sort of normalized reward here that will get fed back to the policy model. It's kind of what's up in the PPO world. In the GRPO world, there's no value model. There's just like the policy model, and then this whole section for the reward has been removed and replaced by group computation, which basically means that the policy model, instead of just outputting one output for one question, right, it will output multiple ones. With these multiple output, it will generate multiple reward, and then you're going to get multiple advantage, which will be used to optimize the policy model. So you kind of bypass the need for a value model. So in GRPO, you still keep the same two model for the reference and the reward model as a PPO. It's the value model that is gone. A reference model is in the paper. They are saying it's a DeepSeek V3 base model. So like this one over there, right? In the algorithm that they show, it's not exactly that. It's like optimized old model after a while. Anyway, and you keep the reward model over here, and the reward model can be a neural network, but it can also just be like some rule-based thing. And in our case, for this paper, it was some rule-based reward functions. And as we're going to see in the code, it's also a bunch of reward function that we have. That's at the high level. The interesting two bits of information, right? In this PPO, look at where the KL divergence is. It's like near the reward side, right? And in our case here, it's not there. It's it's outside of the reward. So we'll see this slight difference in the formula. So if we look at the PPO, what you're trying to do is you're trying to maximize this objective, which is a big formula. It's fairly verbose, but like if you look at this map, it's not that complicated. Like O is your output, Q is your question, R is the reward, A is the advantage term, which is calculated in a specific way. So you're trying to do the mean of like all of the output that you're shooting out there, right? And then you're gonna clip the amount of change that you can have in a particular step, right? So like you have here the P with P at theta for like a specific like output that you have for a specific question. And in this case, this is the model that we're like actively modifying. And this is the previous iteration model. So why we're doing this divided by the previous model is to kind of have a sort of momentum, a bit like with Adam and like these type of optimizer. It's a very different, but like it's the same kind of rough idea. So if you're like been decreasing, you're gonna decrease faster. And if you have been decreasing and then now like you're increasing, right? This like probabilities, you're gonna increase a bit lesser. That's kind of the rough idea. So this is how confident are you from your output, and then this is like your reward, like how much are they worth really, and it's a normalized one. And then we're doing like the minimum between this quantity and this quantity, because in this quantity we don't want to take too big of a step. So if you are above a certain epsilon in any direction, right? So like if you were saying the limiter there, right? And then like you were there previously, so you're only allowed to change like the parameters a bit over here and a bit over there. So if for some reason you're like going crazy and you're trying to put the parameters like way down or way up, it's gonna clip it, and then you're just gonna bring it all the way back to the minimum that you have over here. That's a rough idea here. It's just to avoid like a very erratic movement. So the A here is like the advantage, and it's gained through like this generalized advantage estimation. The reward is normalized with this term, which is the KL divergence term. The KL divergence is like the difference between two distribution, right? And in this case, it's the difference between the ref distribution, the ref parameters, and then the current parameters that we have. The ref here is the DeepSeek V3 base model, and we're going to see in the algorithm it's not always that, but here they're saying the ref is the reference model, which is usually the initial supervised fine tuning model, and base the coefficient of the KL penalty. So you have like these hyperparameter also. In a nutshell, this is PPO. So the change that it did, right? If you look here, they're gonna move this KL divergence thing here to the reference model, but like in not with the reward, and then they're gonna remove that part and that part to just have a group computation. So there's gonna be a bit more averages in there. So if we look at the formula, it's this similar thing, right? Don't freak out. It's exactly the similar thing. There's this different groups. So we're doing like an average of the groups that we're gonna output, and the groups is just like a bunch of output for one given question that you're getting there, right? So here, this is a group. So you have one question, many output. So 1, 2, G, right? And this is for all of the output that you're having, and then you're doing the same thing. You're minimizing. So this we know. This is the clipped thing. This is like the same thing. It's the same thing as before, right? The KL divergence is now here, right? And we're doing minus this because we're maximizing this formula. So it's important to keep track of the maximization versus minimization thing, because usually when it's implemented, you're trying to like have a loss out of it. So you're gonna have to flip some things in the code, but in this case, it's maximizing this formula, right? So you have a minus on the KL divergence here. You have the same story. You have the current parameters, and then the ref, which is the DeepSeek V3 base with the supervised fine tuning. And here they change a bit the formulation, and they are following Schulman over here with this unbiased estimator. So it's this thing, and then you have minus log of this minus 1. In the actual code, it will be a bit different. There's going to be an exponent that we're going to like have to go through to, it's a bit simpler to look at because there's not the logarit in there, but it's a bit different. It's not the exact same formulation. The A here doesn't go through the generalized advantage estimator, right? It's just a formula straight up. So the formula for the A is the following. It's like a normalized kind of a reward. So you have the reward at the current point minus the mean of like the group divided by the standard deviation of the group. So basically the advantage is like how much this reward is good with respect to the whole bunch of output that we have. Is it much better than the group or like the same as the group or like lower than the group? So if we take a look at the overview of like this whole GRPO thing, you have the prompt over there, which is your input. And this is your completion that you are gonna put out there. And then based on the completion, you're gonna output some reward. And the reward is taking a bunch of functions. And then like with these, you're taking the normalized reward over this group. And then you get what we call the advantage. And you do the same thing over here. And then you like sum all of the advantage together. And you have this side that is fixed up. Then what you have is like the calculation for the KL divergence. You have your current policy, you have the reference policy, which is like way back. And then you're trying to like calculate the KL divergence between this and that. And then this is used to, you're subtracting this from like your motion that you're going through with your advantage. And then you calculate the mean, and then you have like the objective that you're trying to optimize. So that's a good overview of the whole thing. So take note of completion, prompt, reward, advantage, KL divergence. These terms will come back into the code. If we look at the actual pseudocode from the DeepSeek Math paper, you have like this setup, this 12-step. So you have the initialization of the policy model from like the first base model that you have. And then you're doing multiple iteration. And in each iteration, the ref is changing a bit, right? This is in like this pseudocode, but it doesn't match exactly the rest of the paper. So I'm not sure if this is right or if like this init is actually like the actual base. But yeah, there's a ref which is limiting the amount of changes that you can have with the model as it goes through the multiple optimization step. Anyway, so you have that, and then this is the step that you're doing in each of the iteration. You sample a batch of data, and then you try to update the old policy model with like this one, right? The new one that you have. So in each of the step, the old policy will change. So it's like a different checkpoint, right? You have the ref that is all the way there, and then you have your old that is over here, right? And then you have your current that you're trying to modify in this current step. So the distance between these two is like one step, right? And then distance between these two is like M step. This is what they're saying in this pseudocode, right? Okay, so this is what we have. And then we sample G output from one question, right? For each question in a data set, for one question, you have a group. And then what we do is we can compute the reward like we saw. And then with the reward, we can compute like the advantage for like each of the tokens. So with the group relative advantage estimation, this formula that we saw. And then here we're doing the GRPO optimization step. So update the policy model P of theta by maximizing the GRPO objective. And then you iterate on this. And that's it. That's the, in a nutshell, this is what every terms mean in this thing. I suggest you check out like the PPO algorithm. If you understand the PPO, the GRPO is simpler. So let's jump into the code from Hugging Face now. The code is all open source, so we can take a look at everything. And like their thing is the GRPO Trainer. It's still in active development. You can still use it, but that's what they have put out there. Great work to the team. And how you use it is like this. So you import GRPO Trainer from TRL, and then this is their API. You decide which like base model you want to use to be able to do the GRPO or reinforcement learning training on it. And then you tell it what reward function you want. Let's dive into the code in a few. Before that, let's look at like their loss that they're gonna use in the GRPO training regimen. So this is what they decide to use. And here, watch out, they're using loss, not an objecting function that they're trying to maximize. They're trying to minimize the loss. So you have to flip a bunch of numbers. So basically just put the minus in front and you should be good to go. There's two things that they change. Here you see you have the old that you're supposed to keep in memory, but instead of that, they can just like slap a no grad to one of the variable and it should be good to go. So this is the same thing as old. And over here, in this one, they have a clip because they say in the original paper, the formulation is generalized to account for multiple updates after each generation by leveraging the clip surrogate objective. What they're saying is that in TRL, we only do one update per generation, so we can omit and simplify the loss to the first form, so not to have this form over here. So this is actually what we're gonna see in the paper. Second thing is that in the paper, it's probabilities, right? Now we're dealing mostly with log probabilities, right? So log probabilities, this is what you're gonna see in most of the scientific packages that has to deal with that because it's just faster, more accurate, it's simple. Log probabilities are much easier to work with than directly having the probabilities. So keep that in mind because this will change the formulation in the code. So if we dive deeper into the code, our entry point is prediction step. There's this function, prepare input, that is doing a lot of heavy lifting. We're gonna see it in a few. Where we're actually doing GRPO is here in the self-compute loss thing, right? And then we're taking the mean of that and we're returning the mean loss over there. So if you go into compute loss, this is the main like GRPO thing. We are doing a bunch of setup over there. And after that, we're getting our per token log probabilities with this function over there in here. And this function, the only point of it is to get the per token log probabilities and return them to the main GRPO function. So we're doing this over there, token by token, we get the token log prob. We append it to our nice list over here, and then we're returning it as a tensor. That's very important. So at this point in time, every log PS that you're seeing is a log probability. So it will change the information that we have in our formula. Step one, KL divergence. So we have our two things. We have our current log prob and our reference log prob that was in memory. And we're doing this formula. So it's exponent of ref minus current minus ref minus current, right? You have to see it with the logs in it. So let's go and do the change from here to the other thing and see what we need to change in the formula in order to retain the same thing. So what I mean by that is that at this point in time, we don't have this. We have log of this, right? Log of ref, right? Divided by log of theta minus log of ref divided by log of theta minus 1. What you want to do here is to reverse this log and then simplify the formula so you have one thing to do. So here you're putting e to the log, right? Same thing here, e to the log, and same thing over there, e to the log and e to the log. And now with the property that we have over there, we can play around it a bit. So when you have e and e to something, you can do the following. You can do e to the log ref minus log theta, right? So this is good. This is exactly what we see over there, right? You see e to the log ref minus log theta. And over there, what we have is we're gonna have minus, and then this, we can simplify it like this, log of e to the log ref, right? And then minus e to, to log e to the log theta minus 1. Perfect. Now we can simplify a bunch of stuff. So we're going to use that one over here. So we're going to do a minus, and then we're going to take this. We're going to have log ref, right, in here, times log, when I say log, I mean ln, right? And in here minus the same thing, theta, well, log theta times log of e again, right? Minus 1. So these one, they become a 1, this one become a 1. So what you end up with is minus log ref minus log theta minus 1. Voila. So if you look back, here we have minus log ref minus log theta. Okay, minus 1. And after that, we get our magically our advantage that is over here. This advantage comes from the prepare input. So we're going to see it in a few. But after that, what we're doing is the same thing that we need to do with the token loss time advantage over there, right? These, we don't have that. We have log of the theta divided by the log of old. And then we're just taking the e over there. So we're doing e, and then it's going to be log theta minus log of old, like this, time the advantage. Advantage doesn't change. And then here we're doing our minus, right? So we're doing minus all of this, and it's minus this bit that we just did, right? Minus that. And after that, we're kind of done. So the only thing that is left to do is this last part over here with these two, this one, and then that one. So that one is happening, the internal one is happening here, right? And then the other one is happening there, like this with the mean. So this one and that one. And if you see, there's a completion mask that is popped up out of nowhere. So this completion mask is a binary mask. So we have 0 and 1s. And what it means is that a 0, it's when you're at before the end of sequence, so in the prompt technically. And 1 is when you're out of this, so you should take into consideration only the things that are out of that. So we're calculating the loss over everything, right? But we should only take into consideration the things that are after the end of sequence. We're gonna see that in a few in the prepare input. So here we are. We don't need to go into like much in here. What we need to check out mainly is this, the completion mask over there. Right, we calculate the sequence in this and everything, and here we're trying to mask everything after the first end of sequence token. So this is where the binary mask comes from. We're using the end of sequence indices to mask the right stuff, and we're creating our 0 and 1 mask over here. So that's perfect. Now if you go back to the reward, so this part is where like the reward things are happening, right? The reward you should think of them is like you have a block, and then you're shoving your output through that block, and it will return you a reward directly. So the rewards function are these blocks over there, right? Each of these are a reward function, and then you're going to take like this normalization to get the advantage for each of them. If we look over here, we're going to iterate, and this is where we're going to call our reward function with our prompt, completion, whatever the argument that is needed, you put it there, and you get your output reward, you like stack them up, and then you're going to be able to calculate your mean group reward, your mean standard deviation reward, and then you're going to be doing our R, which is the reward, minus the mean group with reward, divided by the standard deviation plus an epsilon to not divide by 0. So the reward, you can customize them if you want to. So you can like create your own reward function like we saw at the top. Let's say here for rewarding longer completion. You can have another one with specific format, and you're using regex in there, and or a reward here for completion based on the reference or something like that. You can put anything that match your the specific behavior that you want your model to do reinforcement learning on. And that's this. After that, it's mainly just logging, and we're done. Now that we know what is going on, let's go into the specific penalty term KL divergence within GRPO and how it differs from the implementation in the past, namely the one in the PPO algorithm. That penalty term is very important to anchor the whole reinforcement learning methodology into a parameter space that is not too different from the reference model, which is a non-fine-tuned model. The part that is interesting for us in this whole thing is this little part with the KL divergence. In PPO, it was implemented in a certain way, and it's more around the reward function. And then in GRPO, it's implemented in another way. Already there's some design decision that was made. Why didn't they jam it into the reward function? Maybe it was easier to code because here you have many reward and you have to take like the average and stuff. It would be easier if it was out of this mess versus here they can directly be added to like the single reward that is being outputted. If we take a look at like what does the KL divergence look like on the PPO side, you have this term over here. So it's in the reward variable, and then you have this hyperparameter beta that control how much of this you have to account for. So we have log of some probability over here divided by another set of probability. This is a reference model, and then this is the current model that we're optimizing. So on the GRPO side, what we have is like the reference model probabilities divided by the current model minus the log of the reference divided by the current model. So there's a few things that are different in this case. The ref and then the current model are like switch over here compared to that part, and the form doesn't really look like the form that we're accustomed to for KL divergence. Before we jump into the blog post, I just want to recap what KL divergence in a broad manner. If you want to have like a good step-by-step example of like what KL divergence is, how does it differ from cross entropy, and what's like the numerical differences between like the different element, I strongly suggest Cyrano Academy. It has a video on this that is super good. But in a nutshell, you have a probability distribution over here, right, for a bunch of output that you can have, and you have a sequence that is the current one, right? And then like from this sequence, it's sampled from some sort of probability distribution, and in this case, this is like a die that has 5 faces, and this one corresponds to this, right? So this one is actually the thing that is producing the sequence. But let's say you didn't know that, and then you have another probability distribution, right? You have another die over there and another die over there. And then with their specific probability distribution, you're asking how different like this sequence is from these. Are they pretty similar or are they pretty different? It's important in our case for reinforcement learning for the PPO and the GRPO because we want to constrain the model so that like it doesn't differ too much from a base model, that a reference model that we're keeping an anchor on. Right, that's the whole idea, so that like the parameters are not changing like crazy. It still stay close, right? And then like if the performance is much better, then it has more leeway to move away from the reference model. So this is just to stabilize a bit the reinforcement learning. There's many ways you can calculate these differences with probabilities, right? You just multiply them. The issue with probabilities, the raw one, is that you get like very, very small numbers. And if you have many of these parameters, you're gonna get like very close to 0, which in some case will literally be 0 and will be difficult to work with. So usually you don't work with raw probabilities, you work with log probabilities. The thing with the logs is that if you take the log of all of this, you can have additions instead. And additions is fantastic. It's a bit faster to calculate than multiplication. Plus, it doesn't, in this specific case with cross entropy, it doesn't go into the problem like very, very small numbers. It will be like a reasonable number. KL divergence, take this a bit further. It's always positive, and then you have it anchor between 0 and like infinity, and it's a measure of the differences between the two things. So here, like one of the way you can think about it is like it's the cross entropy minus the entropy of the first probability distribution, that is the anchor one. And then you can like switch like the cross entropy here, and then you're gonna get this minus that, the entropy, you're gonna get your numbers here, and you can be able to say how different the things are. KL divergence at 0 if like the probability distribution is the same in like both things that you're comparing to. The both probability distribution are exactly similar. The more the number is bigger, the more they are different. So that's in a nutshell, right? There's many ways to write the KL divergence that are valid. The initial version is this one, right? If you have all the x's, and then if you have like the actual probability distribution, this is how you should write it. With cross entropy, it's written like this. So it's very similar to this form, and actually you can recover this form using this. So you have like KL divergence equal to the cross entropy of P and Q, which are the two probability distribution, minus the entropy here. So very, very useful concept in machine learning, because we are gonna handle like parameters that have like probabilities or log probabilities that are stored, that then you can compare against another model. So you can compare like model like this, and here you see an example in this BERT paper where they use KL divergence again over here in some of their formula. So it's pretty widely used. The thing here is that the implementation will differ, and you have to understand a bit the trade-off of all of this. We cannot use the formula directly as is written, right? You cannot go torch distribution and try to use KL divergence directly. It's going to be one, so most of the case impossible. Second, very wasteful, because you don't need to be like that accurate. It's usually a penalty term that you're imposing on your training for your model. So it's fine if like it's not exactly the number that the actual KL divergence will have outputted. A good estimation is good enough here. So this is why you're seeing like these implementation over here versus these ones. There's also a third one, right? But like all of them are valid. Some of them are biased, some have a higher variance. You have just to watch out for these trade-offs. And if you look at the implementation, like but here it's implemented over here like this in the open source implementation of Hugging Face. And you can see here we have our log probability for the reference, our log probability for the current one. And here we're using an exponent because we have log probabilities so that we can recover the actual probabilities minus one. So fairly easy to implement. The implementation is not the hard part here. In the paper, they are referencing Schulman, which is not the scientific paper that they're referencing. They're referencing a blog post from the dude. This person is one of the co-founder of OpenAI, right? And pretty important researcher in the field. He was a researcher at Anthropic. So it's in the blog section that we're gonna see is a contribution. And the blog section, there's 3 things in the blog from 2020. And one of them is this thing, which is interesting. So we're gonna go to the blog. It's linked in the description if you want to take a look at it. I just annotated a bit, but he start with like this definition of KL divergence, which is basically the expectation of the sample x from Q of this quantity, right? Log Qx divided by Px, and Q and P are probability distribution. So one thing that he's saying is that usually we're implementing KL divergence just by implementing it on log Q and divide by P on some amount of sampling data that we have, so that we can do this kind of Monte Carlo estimation. That's the implementation that the PPO algorithm is using. So it's log of Q on P. So a good estimator that they're saying is this, right? It is unbiased, right? This one. A bias estimator is a bias if like the expectation of the estimator minus the actual value. If it's not equal to 0, then like it's a bias estimator. In our case, for our estimator, which is log Q on P, if we take the expectation minus QL, it's exactly the same. So if you have enough sample, the two things will be very similar. So here you have to watch out how it is doing the nomenclature, because is defining a variable R, which is a ratio, P on Q, not Q on P. So this means that like log of Q on P will be minus log R. It will just be easier after that to write the rest of the formulas for the unbiased estimator. This is why it's kind of flipped in our implementation in the GRPO. Here, like this is supposed to be P, this is supposed to be Q, this is flipped versus like this implementation in PPO. This one, although it's not biased, it has high variance because some of the numbers are going to be negative because of the log. Log of 0 point something will be negative. Well, the actual KL divergence is not negative. It's between 0, like we've seen, and infinity. So if you have that over here, and then for some of the sample, you're going to have like the P being smaller than the Q, then you're going to get something that is between 0 and 1, right? And then log of this will be negative. And then once you're going to look at the variance over here, if you have a negative number minus the actual true KL value, which be between 0 and infinity, you're going to get something that is negative. So it's going to go a bit over there, you square it. So this setup empirically increased the variance of this estimator. So what they're saying here is that you can use something else that has lower variance. It's biased, but this is kind of better, right? And it's like log of the ratio that we see in P on Q. There's many ways of writing it depending on like the different log properties that you're using. But roughly it's like log of R exponent 2 divided by 2. Like that's kind of how it's set up. So this is biased because the expectation of this quantity minus QL is not equal to 0, because this is supposed to be E to the log of Q on P. Thing that he's saying in this blog post is that empirically, when he tested it out, it's a bit more stable. And like, yes, it's biased, but it's not that biased. And we know when it's going to be more biased. There's a whole section here that I encourage you to read and go on it slowly about this specific estimator being a F divergence. So KL divergence is a F divergence. This one is also F divergence because of the specific form that it's taking, which the form look like this, right? There's a function and there's a P and a Q over there. In these family of function, the F divergence ones, there's specific properties of them. And one of them is that if P and Q are pretty similar, right? Like together, any function, any F divergence function will look like a KL divergence. Like they will look very, very similar than the two. So this is why this specific quantity will have a lower variance, because it's like very close to this. If this thing is set up as P and Q being roughly similar. In the case of reinforcement learning, yes, it will be. And in the specific case in which we are using it, P and the Q should be roughly similar. Remember, here we have our reference parameter set, and then we have our current ones. This one comes from this one, so it should not be like crazy different. So this is where it's at. So now we have two type of function that you could use as an estimator for KL divergence, like the minus log of R, and this specific one, which is the log of R exponent 2 divided by 2. The third one that it did, the K3, which is the one that was used in GRPO, to make it, we're not using the second one, which is biased. We're going to use the first one, which is unbiased but has high variance, and we're going to try to lower the variance. And what they're saying is that one way to lower the variance is with the control variate. In a nutshell, what it is, a control variate, is if you have an unbiased estimator, let's call it M over here, and then you add to it a quantity that has zero expectation, it will not change the expectation, as if it doesn't do anything to this biasness. In this case, let's say you have another estimator, which is T, and it has an expectation of tau, and then we're going to do T minus tau. Technically, this will lead to an expectation of 0, and if you multiply this expectation of 0 by whatever number, doesn't matter, right? So you get this formula of how you can modify with this variate a non-biased estimator, and then have the resulting M star unbiased estimator. If you set this properly, you can reduce the variance while keeping the bias in check. In our case, the quantity that we have that is guaranteed to have zero expectation is this one. So this is our T, this is our tau, so we have R minus 1. And like you see here, we have the lambda, which is similar to the C that we just saw. And we can set the C to the lambda to 1, and you should be good to go. If you set the control variate to be inversely correlated to the other thing, you're gonna have something with which lowered the variance. That's one of the property of that control variate if you set it up like this. And by doing this, they're gonna add the log of Q on P plus this control variate, which is exactly this term. Remember, R is P on Q, right? And here this quantity was log of Q on P. But if you switch these two to have like, it will be similar to having minus log of P on Q. And this is our ratio R, so it's going to be minus log of R here. And then we have our R over there also, R-1. So it's this quantity, this estimator that is unbiased, has high variance of the KL divergence, plus its control variant. So that's our K3. So if we recap, we have R over here. K1 is this one. This is what is being used in PPO. K2 is this. It's not being used in anything PPO or GRPO. Some other implementation, I think the author said that he was using it. This is the thing that we're using in GRPO. So Schulman ran a few experiments here. I'm just going to show you the code. So he did a bunch of simulation. You have P and Q, which are like distribution that are normal with different mean. The standard deviation stay the same. It's just the mean that is changing. And then like he's using the KL divergence, which is the true version of KL divergence from PyTorch over here with the formula that we saw previously. And then we have here or R, which is the log probability that are divided. And this is just using the property of the logarithm to make it nicer to calculate. Here is our K1, K2, and K3 over there. And at this point, there is going to run the simulation on 10 million samples. And with this, with the mean and the standard deviation, they will be able to see how they are different from the true KL divergence. So this is what we have at the top. We have a 0 for Q in terms of mean, and P we have a 0.1. So we create kind of this type of differences. The KL divergence to be very small because they're very, very similar. Remember, a KL divergence of 0, exactly the same probability distribution. Big number, very different. In this other case, they're changing the P from 0.1 to 1, so it's shifted, right? Same standard deviation. And in this case, the KL divergence will be of 0.5. If we look at the performance of K1, K2, and K3, K2 has some bias. The other one doesn't have any biases because they're unbiased estimator. And what you see here is that K1 is good, but it has high variance, and K2 has low bias, but still has some bias over here. What this means is that K2 is good enough. It's not something that is outlandish, but this is when the KL divergence is very small. As the KL divergence become very, very big, you can start to see that the bias of K2 start to creep up. Its variance is good still, but the biases start to be kind of significant, right? So this is when we have more and more different probability distribution. In the case of K3, it's still good. It's still unbiased in both cases, right? Its variance is lesser than K1. And in this case, like the difference is not that insane, but in the first case, it was very, very significant. So we are concluding here by saying like K3 is the better estimator that you should be choosing. And voila! You now have a pretty good understanding of what is going on in DeepSeek R1 and how it works behind the hood. Maybe a bit too much. I'll hang around a bit for questions, so don't hesitate to leave them in the comment section. Have a great week everyone, and see you in the next video.